In this video, we will be taking a look at the basics of flip simulation. In order for us to get a good understanding of the resolution as well as the domain settings of a simulation, we will be making a small example scene of a flip tank containing a rotating donut, which we will then cache out to disk. So let's get started. First, the easiest way for us to make a flip tank and really any flip container within Houdini is to use the shelf tools. Now, by default, you will be coming in on the lights and camera tab, but you want to head over to the particles fluid tab. Here you will find the flip tank option, and you just press that and hit enter, and the option for it comes up. Now this creates a bunch of nodes for us within Houdini. Right, we have our simulation network and also a bunch of geometry nodes. Now the flip tank initial is basically creating the source for this water simulation. Then flip tank fluid imports all of our simulations, and fluid interior is used for render purposes, so right now we don't need that and I'm just going to delete it. Cool. So let's look at the source first and see how all of this is defined. We go into the flip tank initial. We will see that there's an object merge in case you have collisions. Right now we don't have any collisions, so we can actually just delete this. Now the ocean source, here called wave tank, is really the object that defines and sources and builds all of these tank solutions within Houdini. Later on, when we will be looking at guided simulations and that kind of stuff, they also use the same node. So here this node defines the domain of our simulation. So if we would make this box a lot bigger, our simulation gets a lot bigger as well, right? So the settings for the domain, all of this is driven from our ocean source. Now resolution, oversampling, all of these things, these are all linked to our simulation network, right? So really the wave tank is setting up our boundary box and make sure that we fill it with particles where we need particles, and make sure that the initial fields and everything is being exported to the simulation the way Houdini likes it. Okay. One additional thing that can be done here for now is changing the wave level, the water level, if you want to. By default, 0 is pretty much the correct value to choose. But if you would ever run into the situation where you have to change the water level and, for example, simulate a little puddle on a 2-meter high pedestal, you could change it here, right? So this node sets up our source and gives us the confinements for our simulation. Now down here, we just split out the particles and the surface field if we do narrowband, and these are just hooks that are set up for Houdini to pick them up within the simulation network. And normally and usually you should just not touch those. Houdini needs them, and that's all you need to care about. All the settings you need are on the ocean source. All right, let's head into the simulation network and see what's going on there. So the basic flip simulation network is actually really simple, and that is for very basic simulation. All you need to make a flip simulation work is a flip object and a flip solver. Everything else is just nice things to make the flip look cooler, but this is an effective and working flip simulation, as we can see when I hit play. Right, we have our water, we get some moving things down here, but we have a full-on water simulation. So let's take a closer look at the flip object, which actually contains the simulation. If we look at the geometry spreadsheet, we will see that under the flip tank, which is just a flip object called flip tank, we have a bunch of different things. We have our geometry container, which contains all our points, all their attributes, all of that good stuff right here. And then we also have a bunch of volumes. We have our collision volumes, collision velocity volumes, our surface and velocity volumes, our viscosity volumes. All of these guys live on this flip object. Now, here it is very important to establish a base fundamental knowledge of the flip solver, and that is that a flip solver is a volume solver, right? So it does not solve like a pop solver. It does not solve anything on the points. The points are there to carry a bunch of attributes to carry a bunch of data and to visualize and to be high resolution, to be a good representation of what the solver does. Right? We need these particles to have detail in the mesh and to have a lot of information to output. But what the solver does is it takes all of these points and then projects them into the volumes. Right? For example, all of these velocity attributes, they get projected into the velocity volume. Then all of these fields get solved, they get vectored, they get calculated, determines where the water should go. And then after that, it updates the velocity field, then it vects your particles and reprojects all of those attributes back onto the points, right? So it's very important to understand that Flip visualizes points for you. We use the points for meshing, we use the points for everything down the line, but internally a Flip solver simply works on volumes, right? So it's always important to make sure that your volumes are there and your volumes are stable. Now on the Flip object itself, we can see a bunch of settings here for resolutions, physical settings, initial data, all of them, right? So let's go over the basics of resolution settings on Flip. Now compared to a standard, for example, Pyro solver with a smoke object, which has 1 resolution setting, Houdini comes in with 3 flips or flip settings, right? Which is quite a bit more and makes it a little bit more complicated. But in the end of the day, it is very straightforward. And that is, you have particle separation, which is the resolution of the simulation, right? That is the main scale. That's the main thing you want to change to affect the rest of your sim. So if we would go 0.2 here, you would see a lot fewer points. Everything is lower res, right? So let's put this back to 0.075. Right underneath that, we have particle radius scale. So the particle radius scale makes the p-scale of these particles bigger, makes their influence bigger. So if you have a very high volume simulation where you want very little small detail, you can increase the radius here or decrease it respectively. Honestly, I find simulations go quite haywire and become very unpredictable as soon as you start messing with this value. So I normally just leave this by default to 1.2, and the times I touch this value in my career, I can literally count on my fingers, and none of the times it worked out. So let's just leave this as is. Now grid scale is a very, very interesting value. Grid scale comes back to the idea that the solve of the Flip is done on volumes, right? Which means we need to carry all of those grids. We need to have all of that data here. Now grid scale defines the resolution of all of these volumes. We set this to 0.1 for ease, and we look at the division size of, for example, the velocity field. We see that it's 0.2, which is your particle separation multiplied by your grid scale. Set this to 5, it'll be 0.5. Now, the reason this is important is because Houdini solves at a lower resolution than what you're actually simulating at. Now, that is a very, very good thing in most cases, because you don't need as many voxels as you need particles in order to describe a really cool motion, right? You can have a really high resolution splash, but you don't have to have these super crazy high resolution volumes. And especially looking at this, we can see there's quite a few of these volumes. So if all of these are super high res, your simulation is going to take ages, right? So Houdini by default said, hey, let's just simulate our volumes at double the resolution than what the user wants the final resolution to be. And because we project everything back to points, we can just have more points than voxels, filling in these gaps, giving that additional breakup, giving that additional detail, making things look like they're very high resolution with less costs up front. Right underneath the grid scale, we find the part collision separation. Now, collision separation is a fun one. It is there mainly because often if you deal with very thin collisions, the collision field is just not high resolution enough to capture that. And you get these holes and your water flows through your holes and you're wondering what's going on. And you're like, oh, I need to increase my resolution and I need to decrease my grid scale and all of that. And in reality, all your volumes are working. It's just your collisions are not precise enough to meet. So what SideFX introduced is this checkbox. And this checkbox, compared to everything else, is actually not a multiplier, right? So this is not a multiplier of your particle separations. It just hard sets the resolution of everything in your collision field to whatever you type in here, right? So if you need to get really, really precise collisions, you can just oversample the collision field and leave everything else at a grid scale of 2, and you will be just fine, right? So instead of oversampling all your fields, check if maybe your collisions are the only thing that need a little bit of boost in the resolution. Now, right underneath that is something that's a bit strange and a bit different from all the other solvers within Houdini, and that is we have our closed boundary options. Now, again, if we bring up a smoke object, for example, we see those exact same settings here. And they work the same way, right? If I don't close my boundaries, the water will just go out to the edges and just disappear when it leaves my container. As soon as I close those boundaries, everything is good, right? And my water can't escape this box. It collides with all of these surfaces. And if we, for example, just for fun, turn off set negative, then the water runs out of this area and nowhere else, right? And we're slowly starting to leak water. Now, what is strange and what is different is that, for example, the smoke object, all the boundary layer settings, like where the box ends, is right on the object. So the object defines how big the area of the simulation is. With flip simulations, that is not the case, right? With flip simulations, to actually find out what these values are and change them, we need to go to the flip solver, over to volume motion, and here on the volume limits, we now see that we have the box size and box center options that we are used to. Now, in our case, because we used the tools that come with Houdini by using the flip tank option, these are automatically linked to our initial wave tank, right? So that goes back to our geometry node here, really controlling the size of our simulation and all of that living here, right? Now, as you can see here, the resolution that this guy operates at, that's coming from the dot network. So it's just the size that's being driven, which then feeds in here. All right, so if you're looking for boundary layers, especially if you make a new flip solver and you're like on a new flip object, right, and you're building stuff from scratch, don't go looking for how big your box is, anything on the object. Remember, flip solver, volume motion, volume limits. Cool. So the other settings on the flip object are the initial data settings. So the initial data settings are really only needed if you're wanting to start out with an initial field, just like everywhere else. But there is a few input type options that Houdini comes with. So by default, it will use narrowband, which is a very efficient way of simulating ocean tanks, or well, just tanks filled with water. If I change the background to dark, see stuff here, we can see that the volume, our simulation container, right, is empty at the bottom. Now the reason for that is narrowband simulations. Again, because the solver is all volume based, but we're visualizing and we're operating on particles, SideFX came up with a really nice solution of just removing all the particles that are not close to the surface of our simulation. Because all these particles are just used for detail, they're used for extra meshing resolution and to carry very precise attributes later down the line, we don't need them down here. All of these particles down here, they are just wasted. They slow down our computing, right? So with narrowband, we are removing those. If I switch this over to a particle field, then we see that this whole container now is full of particles, and we simulate all of them, and all of them get advected, and all of them get sampled, and we're adding a lot of overhead to our simulation, right? So unless it's absolutely impossible, simulate your things with narrowband. It is just more efficient, and it's better for you to run. And by default, it needs the initial particles as well as a surface layer just for Houdini to have that initialed so that it can run the narrowband. If I would remove this, it would still work, but Houdini really prefers having that field initialized because now everything drops down, right? That is a requirement that only narrowband has. Particle volume, particle field, for example, does not need the surface layer, right? Switch that back to narrowband. Then on top of that, we have the guide options that are the usual guide options with, you know, all your settings per visualizer here. The only thing here that is really big to keep in mind and to change is if you go over to particles, visualization, by default this is spheres. And spheres is a horrendous way of looking at simulations. It's these big spheres with specular, and they slow down your GPU, they slow down everything, especially once you get to higher resolutions in your simulation. I literally had cases where my whole computer crashed, even though the simulation didn't run yet, just trying to draw the first frame. So visualization, change this to particles, and you can even save this just as the defaults as this is now. That is something very important to keep. Now, like every other object in simulations, this flip object also carries all the physical properties. You have your standards of bouncing, bouncing forward, friction, temperature. Density is a new one. By default, it's 1000, which is the density of water. We will be going into this a little bit more in a later video this week, and in quite some detail in the waterfall tutorial later in this workshop. And viscosity can also be found here. We will be covering viscosity and its different options later in this week as well. Right? And then we have collision objects here, which is just changing some of the settings here. Again, I've never really used this. I would not touch it. I would not change it unless you really have to, right? Yeah, just leave this stuff here. Cool. So let's take a little look at the flip solver and just making sure that we get some basics covered here. And the one thing I want to talk about in this video is just narrowband, because this comes with the sourcing. So we're selecting narrowband as our initial here. And then we also need to go and take a look at the narrowband settings on the solver. Now, these are very bare bone and very simple. The important part here is bandwidth. And bandwidth is just how many voxels of particles should we keep around the surface level, right? So if you increase this, you get more particles. You decrease it, you get less particles. And that's really all you need to have. So for some shots, you might want to do a lot with the particles just underneath the surface and introduce new volumes, new motions, new all of additional attributes, that kind of stuff. So you need more particles, because doing that kind of stuff on the volumes is a pain. But sometimes you don't need to do any of that, and you just need some cool motion. So you might as well simulate less particles, right? Increase your simulation time again and make things faster for yourself by cutting down the amount of particles you are simulating. Then if we look at the substep settings, they are existing on the solver like everywhere else, and we have the standard settings of timescale, is you want to do super fast moving fluids or slow motion fluids. We have minimum substeps and maximum substeps. These are used in condition with, in addition with the CFL conditions here. So basically what that means is, a CFL condition is how many voxels can a particle travel in one step before it needs a new substep in order to resolve that motion more precisely, right? So if we have a very slow moving simulation, leave all of this by default. If we would have a very fast moving simulation, you probably want to up your maximum substeps and maybe lower your CFL a little bit, giving you a more precise simulation, right? But normally I try to keep all of this by default and just make sure my simulation is stable enough without massive substeps, because that just means a massive overhead in the simulation, right? So let's set this all back to default. Cool, so now we know the basics of the flip object, where to set the resolutions, how to set some solver settings, and how to make sure that our narrowband works and that our substeps are nice. And we know where all of that lives. So let's drop in a little collision in here and then export this simulation so that we can look at meshing and whitewater later on, right? So as an animation that we would drop in here, I'm just going to make a torus. Call this guy anim. When we go inside of it, I'll make it a bit smaller, and let's rotate it around the x-axis, right? So maybe 10 degrees per frame, so that we're getting to this kind of animation, right? So the easiest way to make things collide or flip is to use the collision source node. The collision source node is really cool because it calculates your motion blur on your geometry, as well as creating an SDF for you. So if we take a look at that guy, we see that we're generating this volume based on the volume settings here. So we can like lower this guy and make a bit more precise volume. So the way you use this and the way you bring this into the flip solver is by merging both of these together. And then I just use a null as a hook so that I can call this within the solver. So let's just call this collision. And now whatever we change here, my solver will still pick up this null, making sure that I can switch out all my animations, plug in multiple animations, and it will work without an issue. Cool. Inside of our dot network, the way we collide with this now is by using a static object, pointing at our animation, collision, and now we turn on use deforming. One important thing is when you use the collision source, go to collisions, change this mode to volume sample. You already have an SDF generated that you could cache out to disk before you simulate when you have a very heavy collider. So make sure you use it, and the way you do that is by changing the mode to volume sample, okay? And now all we have to do is plug this into the merge and make sure the static object is the left input and the simulation we want to collide with is the right one. Now, sometimes if you use a lot of the Houdini buttons, you will get a static solver. You do not need a static solver. You can just delete this guy. All you need is a static object, right? So if I hit play on this now, we see that the collisions work, and we're getting a donut that's slowly rotating in the water, and everything is working as expected, right? Very simple, straightforward flip simulation. So the way we cache this out, let's not look at that donut, let's look at a nicer one. So the way we cache this out is by going into the flip tank fluid here, which is just a geometry sub. And in here, there is an import flip tank node. And this guy looks at our dot network, looks at our flip tank object, and then brings in a bunch of these objects that we saw contained on the flip object, right? Brings in our geometry, which is just all the particles. And then it also brings in a surface layer, which if we show this guy, this surface layer for flip simulations describes by being in positive values what is outside of water, and with negative values what is inside of the water, standard SDF, but 0 is perfectly the surface, right? So wherever the water is, we're getting a 0 right on this edge, okay? So that's the surface layer, very, very useful, very important to have. And let's go over here and set that back to invisible, and the velocity value matches the velocity. Now one more thing we want to turn on, just because we want to do whitewater with the simulation later, is on the top object we want to go to flip solver, particle motion, vorticity, and turn this on. Now this setting is so important that I actually saved a flip solver as a new version of it internally for me that simply has that turned on by default, because that's definitely something you don't want to forget. Really, the amount of times I had to resim a simulation in production when I started out because I didn't check the vorticity button is kind of embarrassing. So make sure you check that every time you do a water simulation. You never know what you're gonna use this guy for, right? Always have your vorticity turned on. Now in here, the import fluid comes in with all our attributes, comes in with our Houdini volumes of the surface, and our 3 float values describing the velocity vectors, right? Now that gets pumped up directly into a fluid compress node. Looking at this guy, what it does is actually really, really cool. Let's turn this off so we see it better. What it does is it takes all our simulations, brings them in, and now has a few options here. The first one you see is the cold bandwidth. So cold bandwidth takes your surface volume and just kills all the particles that are further away from the surface level than, well, what you describe here, right? So if you want to keep all your particles, you would set this to a 10. If you want to remove as many as possible, set this to a 3. Default is 4, which is quite nice. Unless you really are low on disk space, you can like crank that down a bit more. I like having the extra particles, so leaving this at 4 or maybe even a little bit more is normally what I do. The next option is keep particle attributes. Now Houdini comes in with a bunch of attributes like new apart, previous, has previous, right? All these stop attributes, all of that stuff. And all of these attributes actually stack up quite a lot and keep a lot of space when you don't delete them. So what keep attributes does is it removes all of them, right? And it adds a bunch of detail attributes instead. Now, why it keeps those detail attributes is because Houdini's tools use those later on. And they're very, very useful for that. But because they're detail attributes and not per point attributes, each one of them just has one value. So the data size is really non-existent. But if you keep 5, maybe later on when we get into some custom stuff, maybe 20 additional attributes, each one of them per particle, all of a sudden you have 22,000 additional attributes times 5. That's a relatively low resolution simulation, right? So this data set stacks up really, really quickly. So Houdini here by default deletes everything but the attributes in here, which means if you do custom attributes, you have to make sure to add your attributes in here if you want to keep them outside of the simulation, right? And then it has the packed particles option. Packing particles is just nice, less disk space, it's good, very high resolution simulation. You're adding a little bit to the sim time by packing them, and you're adding a little bit of CPU time in the end by unpacking them. But if you're limited with disk space, it's definitely a really nice option to do. The other thing that this fluid compress does is it takes care of our volumes. So again, if we middle mouse button click on just the import, we see that we have 4 volumes here, right? They're all standard Houdini volumes. But if we click on it after the fluid compresses, we see that we just have 2 VDBs, surface and the volume, our velocity here. And now we see that the velocity is no longer 3 float, 3 scalar volumes, but now it is a single vector volume, right? So this guy converts our volumes to VDBs and then does a vector merge on them. On top of that, it also downgrades them from a 32-bit float to a 16-bit float, which is quite a bit better, right? We don't need 32-bit float in 99.9% of the cases for our volumes, so we might as well save a lot on disk space, right? And then we have a standard file cache node here that's set up by default to run through and cache all this out. And I'm going to do this off screen before we get into this video. Alright, so in this video we covered the very basics of flip simulations. We looked into creating a flip tank, making sure we understand the resolution settings, what all of them mean, making sure we know where our boundaries are set up, sure we know what a narrow band is compared to a normal simulation, and also how we can cache effectively the simulation to disk after we introduce some collisions. I hope you all learned something, and yeah, in the next video we will be talking about meshing the simulation. Thank you.